Have you ever noticed how, for all their incredible intelligence, large language models, or LLMs, can sometimes feel, well, sluggish?
Yeah, like they're thinking really hard, but it takes a while.
Exactly. Like a brilliant mind wading through treacle, especially when you ask them to really dig into a long document or, keep a complex conversation going.
Hmm.
It's a challenge, right? You get this amazing accuracy, but often at the cost of speed and just a ton of computing power. But what if you didn't have to choose?
What if you could have both? The
Mm.
brains and the speed.
Right. What if you could have both?
Well, that's pretty much the breakthrough NVIDIA is talking about with their new Jet-Nemotron family of model.
Jet-Nemotron. Okay.
Yeah, and they're doing it with this really innovative approach called post-neural architecture search, or PostNAS for short.
Just now.
So today we're diving deep into how these researchers are basically building like a rocket-powered brain for AI, models that are super smart and lightning fast.
Okay, so that's our mission for this deep dive then. We're going to unpack the key ideas from NVIDIA's paper, figure out how these new models get this unprecedented efficiency without losing accuracy.
Exactly. It's a significant leap.
Consider this your shortcut to understanding it. We'll pull out the important bits so you really get what's going on.
Felt good.
All right, let's unpack the core challenge first. We know LLMs are powerful, but that self-attention mechanism, it's crucial for understanding context, right?
Absolutely essential.
But it comes with this computational complexity of ON. Now, that sounds very technical. What does ON actually mean for us, using these things?
Right. So ON means basically as the amount of text the model is processing, the context length gets longer.
Okay.
The computation needed doesn't just grow steadily, it explodes exponentially.
Literally. Wow. Yeah.
Think of it like a brilliant librarian.
Yeah.
But for every new sentence you give them, they have to reread and reorganize every single book they've ever seen just to understand that new sentence.
Oh, man, that sounds exhausting and slow.
Exactly. As the pile of books grows, the whole process just grinds down. It creates this huge, long context generation problem, slows down responses, and it also generates a massive key value cache, the KV cache.
KV cache. That's like its working memory.
Precisely. It's the model's working memory, and it just keeps growing.
Yeah.
Like that librarian needing a bigger and bigger desk just for all their notes.
So that ON thing, it's not just math on paper. It's why my, super smart LLM sometimes acts like it's wading through treacle when I feed it a long email to summarize.
That's the reason.
Or why having a really long chat feels like it's costing a fortune to run. That really connects the dots. And for us, that means, well, sluggish models, higher running costs, and it's a real barrier to using AI for these really complex long-form tasks. It's a major roadblock, isn't it?
It absolutely is. It's not just inconvenient. It's a fundamental limit on where and how we can deploy these powerful tools.
Okay, so here's where it gets really interesting then. NVIDIA's Jet-Nemotron models, they're stepping in to tackle this exact problem,
Right.
promising to match, maybe even beat, the accuracy of the big guys, but drastically speed up how fast they generate text.
And the secret isn't just making them bigger or throwing more GPUs at it.
No.
No, it's this whole new design process. Post-neural architecture search. PostNAS.
PostNAS. That sounds like a game changer.
It really is. I mean, the core idea kind of flips the usual script. Normally, building these big LLMs means starting from scratch, right?
Yeah.
Which is hugely expensive, takes ages.
Yeah, it needs massive data sets, tons of compute.
Exactly. But PostNAS, it starts with an already excellent, pre-trained, full attention model, one that's already smart.
Okay.
And then this is the clever bit. It freezes its multi-layer perceptron weights, the MLP weight.
Freezes them, so it locks in the core knowledge.
You got it. Think of the MLP weights as the model's deep down knowledge, its reasoning patterns, its core brilliance. By freezing them, you're basically leveraging that existing high-performance engine without retraining the whole thing.
Ah, so instead of building a whole new race car engine from scratch,
Yeah.
they take a really good one that already exists and then just precisely tune, like, the fuel delivery system to make it super efficient.
That's a great analogy. It captures it perfectly. You're building on existing strength to get new efficiency.
That feels like a really powerful shift. It makes innovating in LLM design way faster, right? And maybe more accessible for folks who aren't, giant tech companies.
Definitely. Lower barrier to entry, less data needed, faster iteration. It's a big deal.
Okay, so how did they actually build this rocket-powered brain? You said PostNAS has pillars.
Right. 4 key pillars in the PostNAS pipeline. Each one adds something crucial to Jet-Nemotron's success. Let's break them down.
Let's do it. Pillar 1.
Pillar 1 is full attention placement and elimination. The big idea here is, look, not all parts of an LLM are equally vital for every task.
Okay, makes sense.
Some of those really heavy, computationally expensive full attention layers, they're critical for high accuracy on certain tough jobs, like retrieval, finding specific facts in lots of text.
Right, where you need pinpoint accuracy.
Exactly. So what PostNAS does, really cleverly, is it automatically learns the best places to put these crucial full attention layers. It figures out where they matter most.
Instead of just scattering them everywhere.
Precisely. And it replaces the less important layers with more efficient, lighter, linear attention. And their research found some surprising things.
Like what?
Well, for a common benchmark, MMLU, they found only about 2 layers were really critical.
Just 2?
Yeah. And for retrieval, maybe 2 or 3. And interestingly, the layers that were key for MMLU weren't always the same ones needed for retrieval.
So it's task specific.
Very much so. But the good news was, if you combine the top layers needed for both MMLU and retrieval, that set often covered what you needed for even harder stuff, like math reasoning.
Okay, so that smart placement, it actually works better than the old way.
Significantly better.
Yeah.
It really boosts accuracy compared to just uniformly spreading full attention around.
Wow. So it's not just having full attention, it's being super strategic, almost surgical about where you put it. That's a huge insight.
It is. It's about efficiency through intelligence, not just brute force.
Okay, so critical layers placed strategically. What's pillar 2?
Pillar 2 is linear attention block selection. So once you know where the full attention needs to go, you need efficient replacements for the other layers, right? These are the linear attention blocks.
Gotcha. Lighter, faster attention.
Exactly. PostNAS systematically checks out different existing options. They tested things like RWK-V7, RetNet, Mamba2, GLA, DeltaNet, a whole bunch.
Like comparison shopping for the best engine parts.
Kind of, yeah. And the winner that emerged was gated DeltaNet.
Gated DeltaNet. What makes it so good?
It's got a couple of tricks. First, a data-dependent gating mechanism, fancy name, but it basically lets the block dynamically decide whether to focus more on the brand new information it's seeing right now or lean more on its memory, its historical context.
So it adapts its focus like a smart filter.
Exactly. And second, it uses something called a delta rule for updating its memory state, which is super efficient. Instead of recalculating everything, it just sort of adds the new bit of information from the current word. Very lightweight.
Okay, so they rigorously tested and picked the best existing efficient block. That makes sense. But you mentioned innovation too, pillar 3.
Right. PostNAS isn't just about picking off the shelf. It also helps design totally new attention blocks. And that brings us to pillar 3, new attention block design featuring the Jet block.
Jet block. Okay, a custom part. What's special about it?
Its main innovation is using dynamic convolution kernels. Now think about, say, an image filter on your phone that's usually static, right? Always does the same thing.
Yeah.
In an LLM, a convolution kernel is kind of like a mini detector for patterns in the text. What makes the Jet block kernels dynamic is that they don't just look for one fixed pattern. They actually adapt their detection abilities based on the specific text they're looking at right now.
Whoa, so the detector changes itself depending on the input.
Exactly. It's like having a filter that intelligently reshapes itself to find the most important details in this specific piece of text. Super flexible. Plus, JetBlock also gets rid of some redundant calculations, some static convolutions for extra efficiency.
And the result? Does JetBlock make a difference?
It does. The paper shows it gives a nice boost in accuracy, especially on math reasoning and retrieval tasks, and it does it with very little extra computational cost.
That's some fine-tuning. It really does sound like building a custom racing engine piece by precise piece. But, okay, we've got smarter attention placement, better linear blocks, even new custom blocks. How does this all add up to that speed we talked about, the real-world performance boost?
Excellent question. And that leads us straight to the fourth and maybe one of the most crucial pillars, hardware-aware architecture search.
Hardware-aware, okay.
So traditionally, when designing models, people often focused on parameter count, how many adjustable knobs the model has. The thinking was always, fewer parameters means a more efficient, faster model.
Yeah, that seems intuitive. Less stuff to compute.
It does, but PostNAS research uncovered something really key. When it comes to actual throughput, especially for long text generation, the KV cache size is often the most critical bottleneck.
The KV cache again, the working memory, not the number of parameters.
Not primarily, no. It was a real aha moment. Because the decoding part of LLMs, generating the next word, is often limited by how fast you can move data in and out of the GPU's memory bandwidth, not just raw calculation power.
Ah, okay.
And smaller KV caches mean you can fit more different sequences, more different conversations or documents onto the GPU memory at the same time and process them in parallel, which directly boosts speed or throughput.
So we were maybe focusing too much on the number of passengers, the parameters, when the real bottleneck was the luggage compartment size, the KV cache.
That's a perfect way to put it. It shifted the focus from a proxy metric, parameter count, to the actual physical constraint, memory bandwidth and KV cache size.
So how did PostNAS use that insight?
Well, instead of just trying to minimize parameters, it optimizes directly for generation throughput on the target hardware, like an NVIDIA H100 GPU.
Yeah.
They essentially fix the KV cache size budget.
Okay, set a limit on the luggage compartment.
Exactly, and then they find the architecture that gives the best accuracy within that fixed cache size, which often means they can actually use more parameters than a baseline model, pack in more passengers to get better accuracy without slowing things down because the memory bottleneck is managed.
That is clever. Optimize the luggage space first, then fit in as many smart passengers as possible. It makes total sense when you put it like that.
It's a fundamental shift in perspective.
Okay, so after all this incredible engineering, these smart placements, new blocks, focusing on the KV cache, what are the results? Did they actually build a rocket, or is it just, a slightly faster turtle? I'm really hoping for rocket.
Oh, definitely rocket. The results are pretty staggering, actually.
Lay it on us.
Okay, generation throughput. Jet-Nemotron 2B. Compared to a similar-sized leading model, Qwen 3 1.7B base, running on NVIDIA H100 GPUs with a really long context, 256,000 tokens.
Yeah.
Jet-Nemotron achieves up to 53.6 times the generation throughput speed.
53 times.
53.6.
Yeah.
And a 6.1x speed up in just processing the initial prompt to pre-filling. It's a massive, massive leap.
Wow. And that's with the smaller KV cache.
Dramatically smaller. Jet-Nemotron 2B uses only about 154 megabytes for its KV cache in that scenario. The Qwen model, over 7,000 megabytes.
7,000. Compared to 154, that's insane.
Huge difference in memory footprint. Huge difference in speed.
Okay, a 53x speed up, tiny memory footprint. But does it still think straight? What about accuracy? Did they sacrifice brains for speed?
That's the other amazing part. No, it's not just fast, it's really accurate too. Jet-Nemotron models match or even exceed the accuracy of leading full attention models. We're talking Qwen 3, Qwen 2.5, Gemma 3, Llama 3.2.
The big names.
Yep. Across a whole range of tough benchmarks. MMLU Pro, math problems, common sense reasoning, retrieval, coding, long context tasks. It holds its own or pulls ahead.
Okay, that combination is powerful.
And get this. It even outperforms some larger mixture of experts models, MOE models like DeepSeek V3 Small and Moonlight, which actually have more parameters overall.
Wait, it beats models with more parameters. How?
On key benchmarks like MMLU and MLU Pro, yes. It really shows that smart architectural design, that PostNAS approach, can be more effective than just throwing more parameters at the problem, especially if those parameters aren't used efficiently, like in some BOVI setups.
Clever design beats brute force scale. That's impressive.
It really is. And it scales pretty well, too. They have a larger Jet-Nemotron 4B model, still maintains a huge 21x throughput advantage over that Qwen baseline while delivering even higher accuracy.
So the approach works at different scales.
Seems so. And maybe the most exciting part for, wider impact, these speedups aren't just for giant data centers with the absolute latest hardware.
Oh. It works on less powerful stuff, too.
Yeah, they tested Jet-Nemotron 2B on things like an NVIDIA Jetson Orin that's for edge devices, and even an older gaming GPU, an RTX 3090.
Yeah.
Still got massive speedups, like 8.8x faster on the Jetson Orin, 6.5x faster on the RTX 3090 compared to a similar baseline model.
That's huge. That makes this kind of advanced AI way more accessible, right? Not just for the cloud giants.
Exactly. It brings high-performance, accurate AI closer to edge computing, to researchers, to developers, without massive budgets.
Wow. Okay, this deep dive really has shown how NVIDIA's Jet-Nemotron, powered by PostNAS and that jet block, it really feels like it's setting a completely new standard. Efficient language models that are the best of both worlds. Super accurate and incredibly fast. It's just clever design winning out.
It absolutely is. And think about the implications. By reusing pre-trained models, by optimizing the architecture so intelligently, this whole approach reduces the cost and the risk involved in developing new, powerful LLMs.
Opens the door for more innovation, maybe from smaller players.
Could do, yeah. Fostering innovation beyond just the biggest labs. And those core insights about which attention layers really matter and how critical KV cache size is for speed, Even more than parameter count, those ideas are likely going to reshape how people design LLMs from now on.
So let's boil it all down. What does this actually mean for you listening right now?
Well, it means the future of AI could look quite different. We can see models that are not just smarter, but way more agile, much cheaper to run, and capable of performing really well on a much wider range of hardware.
From huge servers down to potentially devices in our pockets or cars.
Potentially, yes.
Huh.
It opens the door to making advanced AI truly ubiquitous, powering new applications we probably haven't even thought of yet.
It really makes you wonder, doesn't it? When these incredibly smart large language models are also incredibly fast, and they can run efficiently on hardware that's much more accessible, what happens next?
When new frontiers open up.
Yeah, what kinds of problems can we suddenly tackle? What applications that seemed impossible before suddenly become totally feasible, maybe even commonplace? Where does AI go when it's both